Okay, so this video today will be on just kind of the nature of calculus by special request. So Newton and Leibniz, but Newton probably first, so I'm giving him credit for it, kind of invented calculus, they say. And what he was interested is in how fast things change, because he had his laws of motion, like F equals ma, and he had things like this force of gravity, which is F equals g times the mass of two objects divided by how far away they are squared. And A, acceleration, force is mass times acceleration. Acceleration is how fast velocity changes. And velocity is how fast your position change. And so he needed formulas to say exactly, like, okay, acceleration, how fast something changes. Like, he needed some way to figure out exactly how things change. And the typical way to see how things change is to graph them. So if you graph a function, and the function looks something like this, and you want to know how fast it's changing right at that point, well, you really can't know, because to figure out how fast something's changing, you have to have 2 points. You see, okay, how fast it changed, there's a certain amount of x that it changed, and there's a certain amount of y that it changed. This is the y-axis and the x-axis. And the rate of change is called the slope, and the slope is the change, and they typically represent change with a triangle, the change in y divided by the change in x. But you need 2 points to know how it changes. How do you know how it changes at a single point? That makes no sense. But so what Newton tried to do is come up with a way to figure out how it can change exactly at 1 point. So in other words, the slope of the line right there, it's just hard to draw at that point, not an average with 2 points. So he came up with a really clever thing. He said, okay, let's draw this graph again. So if we want to know the slope right there, which here's y and here's x, then what we can do is take another point a little ways over and call that distance h. So we'll go h over, and they just use the letter h just because it's available. H in the x direction, and then the change in the y direction is the new y, which is the y when x is now x plus h, minus the old y, which is when it was at x. So they typically represent by that the change in y is the new y, which is the y value at x plus this little bit of h, minus the y value at x. So then, the exact slope then, the exact rate of change at that point, is the change in y, which is y at our new x, that's a little bit bigger, minus y of the old x, divided by the change in x, which is just h. And this is going to be the perfect slope as h goes to 0. If we make that distance closer and closer and closer and closer till the points are right on top of each other, we have the perfect slope. And that's what calculus is all about. Giving this formula is the basics for all of calculus, and then you plug in a formula and you let h go to 0, and when h goes to 0 we have the perfect slope at that point, and that's called the limit. And the limit that h goes to 0 is typically written like this: the limit that h goes to 0, what is that function? And so then calculus 1 is all about finding limits and finding the slopes, and the slope then has a special word, the slope, exact slope at a point. They call it the derivative, which is just the slope at a point, how fast something is changing at that point. And this is called differential calculus because a differential is a little tiny bit of something, like h. Here h is our differential, a little tiny difference that we're making, and then we're making that difference go to 0. So it's a tiny difference and it's going to 0. So calculus is all about doing that, like dividing by zeros, and there's clever ways using algebra to get around that, and losing little tiny things and making them go to 0. So it's a cool way to get around the problems of dividing by 0. And so that's what calculus 1 is typically all about in any math class, all about taking derivatives and finding how fast formulas change at a certain slope. So for instance, one of the most common derivative rules is if we have a function like x squared. So let's say we have a function like x squared, which the graph of x squared is just a parabola, it looks like this. So this is y is equal to x squared. The derivative, or the how fast that changes at any point we want, if we want to know what the slope is at the exact point, let's say that's x equals 2, the derivative, which they typically call y prime, you put a little number there by the y, little prime symbol, is 2x. It's a really simple formula. You take the 2 from here, you put it in front of the x, and you take away 1 from the exponent. So the slope there, since that's y equals 2, x equals 2, would be 4. So if we had another thing, like let's say y is equal to 2x to the 4th, the slope would be, take this exponent 4 times 2, so, that'd be y prime, the derivative, would be 4 times 2, which is 8, x, take away 1 from the 4, and you get the third. So, on your own, you can try to take the derivative of y is equal to 3x to the third. So what would y prime be? And again, the way you do it is you take the exponent, multiply it by the number in front, and then take away 1 from the exponent, and that will tell you how fast this is changing at any point on that curve. And that's incredibly useful for things like physics, where you want to know how fast things are changing. And so that's what Calculus 1, the beginning of calculus, is all about. Figuring out how fast things change, how some things change relative to others, and there's all kinds of cool problems you can solve by doing that. Anytime you know the formula for something like x squared or sine of x or any formula that you know, any mathematical formula, you can take the derivative, or there's ways to find the slope, and it all boils down to the formula in the limit that h goes to 0. H is our little bit that we added to x of y of x plus h minus the function at x divided by h. And we plug in our function here, we do some algebra, and we get the derivative. And again, anytime we have something like these, the way it turns out, the way you solve it is the exponent times the number in front times the power x to 1 minus the exponent minus 1. Okay, that's what Calc 1 is about. Then, typically in Calculus 2, which is called integral calculus, it's saying, okay, well that's all kind of good, but what if we have a lot of changes going on and we want to add up the changes? So integral, or integrating, is adding up the changes. So let's say we have our graph again, and here's our function like y equals x squared or something, and it's changing. We want to add up all the changes. That boils down to figuring out the area under the curve. So we want to know the area under the curve, which is adding up the changes. Because if this thing changes more and more and more, there's more area under the curve. If it stops changing, then the area under the curve doesn't increase anymore. And since it's still somewhere up here, we're still getting area, but it's not increasing. And so the area under the curve tells us like how much we have. And that's what integrating does, and it's given by the symbol like this big S kind of thing. And so like the integral of x squared, this is our function x squared, times what's called a little bit of x, they call it dx, which stands for a little bit of x. And we integrate that from like maybe, let's say, from x equals 2 to x equals 8, and that will give us the area underneath the curve from 2 to 8. And it turns out that the fundamental theorem of calculus, which is the whole part of like usually Calc 2 and all of calculus, says that the integral of something, the area under the curve, ends up being that something that you would take the derivative of to get x squared. So if we take, in other words, this is called the antiderivative. If we take the derivative of x cubed over 3 using the rule we just found, this would be 3 times x squared to the 2. So the derivative would be 3x squared, 3 times x to the 2 divided by 3, which is just x squared. So the integral of something is the antiderivative. The answer is what you take the derivative of to get this back. And that's called the fundamental theorem of calculus. It's an amazing thing. How it works is, it's proven that it's true mathematically. It's not obvious it should be true, but it's not obvious to me that the area under the curve depends on what the antiderivative is. The answer is what you take the derivative to get this back. So that's kind of what calculus is all about. The two parts: differential calculus, which is all about finding the slope, like we talked about here, how fast something changes, like how fast gravity changes at a certain point. And then integral calculus, where we want to add up all the changes to figure out over time, if we add up those changes, what overall change do we get? And that's represented by this integral sign here. And it's called integral calculus, and again, it's related to the first part of calculus. This is why we do that one first, because the answer to the integral is the antiderivative of what's in here. It's what we take the derivative of. We take the derivative of this to get this back. So you're working derivatives backwards. And that's what you spend a lot of time in math classes do, just solving this for all different functions and lots of applications. And it's extremely powerful and used in all kinds of, certainly all of physics and chemistry and engineering and economics, and turns out to be extremely useful math to solve lots of problems. So that is my explanation of calculus in a nutshell. Hopefully it made some sense. Thanks for listening.